Hello everyone, welcome to Concepts in Chemistry YouTube channel and also welcome to the NAT question answer series. So as you all know that this type of numerical analysis type of questions usually we see in GATE and IIT-JAM exam. So that's why this series of uh, videos particularly special for GATE and IIT-JAM aspirants, but these questions will also be very helpful for CSA, NET, BARC or any other MSc entrance exam. So we already uploaded one video where we discussed 3 questions. So in this video we will be discussing 3 more questions. So this is the part 2 of NAT series, question answer discussion. So let's see the questions. So NAT question number 4. The boiling point of water at a pressure of 0.5 atm is dash Kelvin. So yeah, given Dayligh's vaporizations of water is 9648 calorie per mole. So we have to find the boiling point of water at 0.5 atm. So to solve this type of questions, we should know the relation or equation. I think many of you already know that Clausius equations or Clausius, one is called Clapeyron equation and the other is Clausius Clapeyron equations. So yeah, this is the Clapeyron equations. dp dt equal to del s bar upon del s v. So this is the Clapeyron equations, and these equations is hold only these equations is applicable for any two-phase system. So two-phase, whether it is liquid, solid, liquid, solid gas, liquid gas, any two-phase, these equations is applicable. That is Clapeyron equations. But the Clausius Clapeyron equations, these equations is applicable only when there is a gas phase. Means this equation also applicable for two-phase system, but among these two phase, one phase should be in vapor or gaseous phase. Then we can use Clausius Clapeyron equations. Otherwise, for any two-phase combinations, we can use this Clapeyron equations. Now that Clausius Clapeyron equation is a modified version of Clapeyron equations, we can establish the Clausius Clapeyron equations from this Clapeyron equations. So we can say Clausius Clapeyron equation is the modified version of Clapeyron equations. So yeah, so dp dt from this we can write del s bar equal to del s bar upon t, you can write, and del v. So since in Clausius Clapeyron equations we have to consider one phase, always one phase is gaseous phase. If we do the details derivations, then we will see that after using proper limit we will get ln p2 upon p1 equal to del h process upon r 1 upon t1 minus 1 upon t2. I have written here process because it is either sublimations means solid to gas, it is either vaporizations means liquid to gas. So if it is liquid and gaseous systems, so then we will write here del H vaporizations. If it is solid and gaseous system means solid gaseous equilibrium, then we have to write here del H sublimation. That's why I, for a general term, I have written here del H process. So whether it is sublimation process or vaporization process. So from these Clapeyron equations, if we do some derivations, so assuming ideal gas behavior, then some details, we have to do some rearrangement in this calculations. So from Clapeyron equations we will get Clausius Clapeyron equations like that, like this: dp dt equal to del H process p RT square. So in this case V gas, if we assume in gaseous behavior among these two equilibrium system, if we assume that in the gaseous phase, if that gaseous gas will behave as ideal, then we can write Vg equal to RT square by P, then P goes to the numerator, and so del A is P upon RT. Now if we write del P upon P, then this dt become this side, and if we do proper limit and integrate these equations, then we will get ln P2 upon P1 equal to del H process, whether it is sublimation or vaporization, upon R. So now see the questions. The question is given that we have to find the boiling point of water at 0.5 atm, and we all know that boiling point of water at 1 atm is 100 degrees centigrade, or you can say 373 Kelvin. This is universal truth, or we all know that boiling point, normal boiling point, this boiling point is called normal boiling point of water is 100 degrees centigrade. So as we all know that the normal boiling point of water is 100 degrees centigrade, that is at 1 atm pressure, or 373 Kelvin. You can say 100 degrees centigrade means 373 Kelvin. So now we have to find the boiling point at 0.5 atm. So we can write, if P1 equal to 1 atm, then T1 equal to 373 Kelvin. When the pressure is 1 atm, then the boiling point of water is 373 Kelvin. Now we have to find the boiling point at 0.5 atm. So we can write P2 equal to 0.5 atm, then we have to find T2. So if we write here P1 equal to 1 atm, then automatically we have to write T1 equal to 373 Kelvin, means at 1 atm boiling point 373 Kelvin. At 0.5 atm, what is the boiling point? Del A is vaporizations, that is molar vaporizations. Enthalpy is given as 9648 calorie per mole. So from Clausius-Clapeyron equations, just this is the Clausius-Clapeyron equations. So in this case, we are considering boiling point of water, means liquid and gaseous phase of water. That's why in this case we have to write del A is vaporization, not sublimations. If there is two phase equilibrium, solid and gaseous, then that is called sublimation. So if we put the value, so P2 is 0.5 and P1 is 1 atm. If we put all these values, so here we have to put R, the value of R in calorie unit, that's why it's 1.987. So if we do the calculations, so after calculations, so T2 will be 354.16 Kelvin, or as a round of figure 354 Kelvin. So if they asked that one after decimal, you have to write 1 point after decimal, then we have to write 354.2. 16 mean we can write 2. So that's yeah, we all know that see when the pressure is decreasing 1 atm to 0.5, the boiling point is decreasing. So when pressure is high, 1 atm pressure is high, means that boiling point is high, and when the pressure is decreases to 0.5 atm, see the boiling point also decreases. So yeah, we all know when the pressure is high, then pressure is greater, then the boiling point of the solvent will be high. If the pressure is low, then the boiling point of the solvent, in this case water, is low. So it is, yeah, it is justified here. That's when we decreasing the pressure, the boiling point of that solvent, in this case water, decreases. So using Clausius-Clapeyron equations, this type of questions, whether it is liquid gaseous equilibrium or whether it is solid gaseous equilibrium, in case of solid gaseous equilibrium, the process is del A is sublimations. All the calculation will be same for any solid gaseous equilibrium. So you have to consider the Clausius-Clapeyron equations, and for any two-phase system, that's Clapeyron equations is applicable. This Clapeyron equation is applicable for any two-phase system, but for Clausius-Clapeyron equations, it is applicable only when the one phase is gaseous. So yeah, so the temperature or the boiling point of water at 0.5 atm is 354.16 Kelvin. So yeah, so let's move to the next questions. Question number 5. So for NH3 gas, yeah, the experimental pressure is 10 atm at 300 Kelvin. So the value of effective pressure at that temperature would be dash atm. So NH3 gas, the experimental pressure is 10 atm and 300 Kelvin at 300 Kelvin. The value of effective pressure at that temperature would be dash atm. So you have to find that effective pressure at same temperature. So assume intermolecular attractive interactions to be negligible, and B, the value of B equal to 3.707 into 10 to the minus 2 liter per mole. So by just by reading the questions, I don't think you got some idea what the questions is from, means where the questions they are asked from, the experimental pressure and the effective pressure. Yeah, if you know that the effective pressure is also known as fugacity, then you can easily solve this question. Just one term. If you know that effective pressure is also known as fugacity, then you can easily solve these questions. If you don't know that effective pressure is also known as fugacity, then I don't think you will solve the questions, because you will stuck in these positions. What is the effective pressure? What is the effective pressure? But effective pressure is also known as fugacity, that is F. So in this case, yeah, we will see what is the expression of fugacity. So in this case, one assumption, that is intermolecular attractive interactions to be negligible, and the value of B is given. So let's see, discuss some basic expressions regarding fugacity, then we will solve the questions. So fugacity or effective pressure, we all know that fugacity is also known as effective pressure. The we can write F equal to phi into P. This P is experimental pressure, so considering ideal behavior or ideal conditions. So if P is the ideal pressure, or you can say in this case experimental pressure, considering ideal behavior of the gas, and F is the effective pressure, that is for real gas. For real system, you can write F is equal to phi P. P is for ideal case pressure, and for real conditions, the pressure is known as fugacity. So for real condition, the pressure or effective pressure is known as fugacity, and this P is normal pressure at ideal conditions. Now F equal to phi into P. This phi is known as fugacity coefficients, and it is defined as ln phi equal to 0 to P limit z minus 1 upon P dP. Z is the compressibility factor, we all know. Now see, if phi is equal to 1, then P and F become equal. Means for ideal gas, we can say for ideal gas phi is equal to 1. For ideal gas phi is equal to 1, that's why P become F, or F become P, you can say. So for ideal gas phi is equal to 1, that's why this F pressure and the P pressure both have the unit of pressure. Sometimes yeah, on questions sometime asked in any competitive exam, that then what is the unit of fugacity? Fugacity or effective pressure is the unit, is has a unit of pressure. So yeah, so it has also the unit of pressure. So yeah, see, for real gas, if we consider 1 mole of real gas, then the equations of that is the van der Waals equations for 1 mole of real gas, P plus A by V square, V minus B RT. So we just put N is equal to 1, P plus N square A by V square, V minus NB is equal to nRT. For 1 mole, we just put here N is equal to 1. So this is the expression of fugacity and pressure relations. Phi is fugacity coefficient. This is the definition of phi, fugacity coefficient. So in the question, NH3 gas is given. So it is a real gas, but the assumption is the assumption is intermolecular attractive interaction to be negligible. So we have to neglect the intermolecular attractive interactions. So this is the van der Waals equation for 1 mole of gas. So if we neglect the attractive interactions, then we have to neglect this term. A is the attractive term and B is the repulsive parameter. A is the attractive parameter and B is repulsive parameter. So in the questions it is said that we have to assume that intermolecular attractive interaction to be negligible. So we can write P plus A upon V square close to P, because we have to neglect means A, we have to neglect this term A upon V square. So this term close to 0. So we can write this term as only P, because in the questions they mention that we have to assume that intermolecular attractive force negligible. So we can write this whole term as P. Now if we rearrange these equations, so PV minus PB is equal to RT. If we divide the equations right side and left side by RT, then PV upon RT minus PB upon RT equal to 1. So PB minus RT minus 1 equal to PB by RT. Now we all know that PV upon RT is the compressibility factor. Z equal to PV upon RT. We all know that we can write Z equal to PV upon RT. So from that, from these previous equations, we can write Z minus 1 is equal to PB upon RT. So Z minus 1 upon P is equal to B by RT. We just try to find expression like that, Z minus 1 upon P. Then we will put in these expressions to find the phi. Then we will automatically get effective pressure, the value of effective pressure or fugacity from these expressions. So now from these whole calculations, we are trying to find this kind of expression. So yeah, for this gas equations, we assume intermolecular attractive force is negligible. That's why we neglect this A by V square term. We only write here P upon P minus B, and after detailed calculations, we found here Z minus 1 by P equal to B upon RT. So this is B upon RT, Z minus 1 upon P. So now from these equations, the fugacity coefficient equations or relations, if we put B upon RT, see Z minus 1 upon P into dP, integration 0 to P, Z minus 1 upon P, in place of this we put here B upon RT into dP. Now B, RT all are constant, so the ln phi, this value of this integration become BP upon RT. So BP upon RT. So now if we write phi, so phi will be exponential BP upon RT. Now from these equations, F equal to phi P, so we can write phi, in place of phi we can write exponential BP upon RT. So P into exponential BP upon RT. For this is the equations for the gas equations where the intermolecular attractive force is negligible, not for this whole equations. This value of F or fugacity is only for the gas in where the intermolecular attractive force is negligible. We can say for these kind of equations, the expression of fugacity coefficient is this, not for these whole equations. Yeah, we can establish we can derive from these equations to evaluate the value of Z minus 1 upon P, then we will get a different. But for F is equal to P exponential BP upon RT, it is only applicable for this kind of gas equations or gas equations, real gas equations where the intermolecular attractive force can be neglected. So yeah, now we got this kind of expressions for a gas where the intermolecular attractive force can be neglected. Now this is the equations. Now see where the data is given. So the data in the questions, P is equal to given. P means that experimental pressure or the pressure at ideal condition is 10 atm. In the questions 10 atm is given. Temperature is 300 Kelvin. And the value of B, the repulsive parameter, is also given 3.707 10 to the power minus 22 minus 2 liter per mole. So if we put the value in the equations, then we will get 10.15 atm. That is the value of F. So F is known as fugacity, also known as effective pressure. So for these questions, the answer is 10.15 atm. So these questions is easy if we know the term effective pressure is also known as fugacity. If we don't know that fugacity and effective pressure are same, then there is a problem, because then it will take time to understand what is this effective pressure, what is this effective pressure. But once we know that effective pressure is also known as fugacity, then we can easily solve this type of questions within a minute. So let's move to the next questions and the last questions. So this is NAT 6 from ionic strength chapter or ionic equilibrium chapter. So ionic strength related questions every time in any competitive exam like CSA, NET, BARC or IIT-JAM or any other exam, question regarding ionic strength every time they ask, every time. So yeah, let's read the question. So X molar of copper sulfate has the same ionic strength as 1 molar solution of KCl. So X molar, X not molar, sorry, it is molal. It is molal, not molar. Small m means molal. X molal of copper sulfate has the same ionic strength as a 1 molar solution of KCl. The value of X is. So the ionic strength of X molal of copper sulfate solution has the same ionic strength of 1 molar of solution of KCl. Then we have to evaluate the value of X. So let's see the answer. So we all know the expression of ionic strength. It is I equal to half summation of mi zeta square. Mi is molality of ith ionic species, charge of ith ionic species is zeta. If we consider aqueous solution means dilute solutions, then we can replace mi by Ci means molar concentration. We can replace molarity by molarity or molar concentration. So since in aqueous solution the solution is dilute, that's why we can use the molarity term in place of molality, and then we can write I is equal to half Ci zeta square. Ci is the molar concentration and here mi is the molar concentration. So we use the first one since the concentration is given as molar unit. So yeah, for KCl in the question given 1 molar solution of KCl, let's find the ionic strength for 1 molar of KCl. So for KCl, if we want to write the ionic strength, then it will become I m, that is molality of K plus, charge of K plus square, molality of Cl minus, charge of Cl minus square. So the concentration or the molality of the KCl is 1 molar. That's why we are putting here 1. Charge is plus 1 square, molality 1, charge is minus 1 square. So half into plus 2 means 1. So the ionic strength of KCl of 1 molar solution is 1. 1 molar solution of KCl, the ionic strength is 1. Now let's try to write the same ionic strength for copper sulfate solutions. So in this case, copper sulfate, molality of copper sulfate plus charge of copper 2 plus molality of sulfide anion into charge of sulfate anion. So in the questions, the given molality is X and we have to find the value of X. So molality is X for copper 2 plus, charge is plus 2 square, molality for sulfate anion SO2 minus is X and charge is minus 2 square. So from this we will get 4x is the ionic strength of copper sulfate solution of X molar. So X molar copper sulfate solution has ionic strength is 4x. Now we have to find the value of X. 1 is the molality, so for every ionic species, cation and anion, the concentration should be same, since these are strong electrolyte. So for copper sulfate also, in the question it is given that X molar copper sulfate solution. That's why in place of molality we are putting here X molar, X molar. Here 1 molar, 1 molar. Charge, here charge plus 2 minus 2. So we will, here we got 4X is the ionic strength of X molar copper sulfate solutions. Now in the questions it is mentioned that the 1 molar solution of KCl has the same ionic strength as X molar solution of copper sulfate. So now we can write here that IKCl equal to ICO4, because they mention in the question that ionic strength of KCl 1 molar, ionic strength of CuSO4 X molar. So is equal. Ionic strength of KCl is equal to the ionic strength of CuSO4, in this case 1 molar, in this case X molar. Now we found, or we calculated, for KCl the ionic strength is 1, and for copper sulfate the ionic strength is 4X. So 1 equal to 4X. We can write from here X is equal to 1 by 4. So it becomes 0.25. So for these questions the answer is 0.25. So yeah, I hope this video will be very helpful for IIT-JAM upcoming GATE exam, and also be very important regarding upcoming CSA NET or bar or any other competitive exam regarding chemical science. So yeah, I hope and I believe that this question answer discussion discussing this question and answers will improve your concepts in chemistry and how to approach to solve this kind of questions. So yeah, that's all for now. Thank you for watching, and yeah, lots of video you will see in our upcoming videos, lots of question answer and lots of concepts in chemistry. So you will see in our upcoming videos. Stay tuned. So thank you again. Stay safe, stay healthy. Bye.